All right, Aaron, we really needed you here today. You let us down. I even brought in a snack, and
Yeah.
they don't know it yet. They don't know it yet, so I'm really upset that you're not here. So anyway, even better than a snack is this theorem that we just covered, but we took our time by each person putting one on the board, and we kind of thought the theorem out for ourselves. You get the bottom line of the theorem. So the theorem is applied to situations where the integral starts at 1 and goes to infinity only. So any other combination of these limits of integration will not work. It has to be 1 here and infinity here. And it has to follow this form. It has dx, of course, and then x to the p. So over here, can you shift over here? Over here are the examples we did. Each of us put one on the board. We found that this one, when p was 2, converged to 1. When p was 3, it converged to 1/2. When p was 1/2, it diverged. And when p was 1/3, it also diverged. So we have made this conclusion. If you have an integral from 1 to infinity of an expression in this form, if p is greater than 1, it converges to 1 over p minus 1, and if p is less than or equal to 1, it diverges. So we did this one the quick way, and we said yes, it follows this example. P, right here is our p, is greater than 1, and it's going to converge to 1/4. All right, so we took a while to mess around with that. You get the quick version. All right. All right, well, I want to finish today by observing an interesting case. I don't know what to call it except an interesting case. Have you got this?
The top, yes.
That's the important part.
Oh, Nitty.
Okay. All right. I want you, in our final, this is our final observation from this chapter. I would like you to look at this interesting case, and I want you to find the graph of y equals 1 over x, and I'm interested in it if x is greater than or equal to 1. So can you sketch y equals 1 over x? That's what we used to call a parent function. It should be in your brain. X is greater than or equal to 1. So if I was good at sketching it, remember 1 over x, it was slash, right. So I'm going to do, I'm going to put in the value from 1, so it's going to look something like that. And then it gets increasingly closer to the y-axis. So I was dramatic. I drew a long part of the x-axis, and you can see it getting closer and closer. What I'm going to do with that, it starts abruptly here and goes forever that way. Today, to put the icing on the cake, we are going to take
Is that a hint on what the snack is?
No, there's no cake. When we take this and revolve this around the x-axis, what does the figure look like? So if I
Across
take
the
that-
X?
The x-axis. So this is going to come out toward the board, and this part will mimic this part. And remember, it's a revolution. It's a solid of revolution. So what's the shape? What's it look like as a 3D figure?
Oh, do you put a circle at the end of
Yeah. Right, because it's been
it?
revolved.
Like a horn?
It is. In fact, it is a very famous horn. They named it, and any mathematician anywhere would know it. It is
Dinah?
Gabriel's horn.
Horn is better.
What'd you say?
Gabriel's
Molly's
horn
brother.
is the name of this figure. What I want to show you of interest is something about a limit, an improper limit that we've been looking at. So recall how we used to do that? We used to take a disk from inside. We call them disks. And they were washers when they had holes in them, but this is a solid disk. And we took an integral and we would pull them all together from 1 to how far? if we took this all the way from the beginning to the end, would it not go to infinity? So there's an old friend, an improper integral, and what follows that, 1 to infinity of, and remember the area of one of my discs is pi r squared, and we're going to add them up, and they are dx problems. Their thickness is on the x-axis, they're lining up on the x-axis. So the r is represented by this yellow line, and that is the length right here, which is y, but we know y is 1 over x. So this is really 1 over x squared. So pi, 1 over x quantity squared. So we just talked about that. That is that a convergent friend of ours or a divergent friend of ours? According to the theorem I just looked at.
Conversion.
It's convergent, and what does it converge to?
1.
1 over, because this p is 2, and it'll converge to 1 over p minus 1, which is 1 over 1, or 1. All right, so very interesting to think of this because, I'm sorry, not 1, that is 1, but I forgot the pi. So the pi comes along for the ride, so we have 1 times pi for pi. So if I was to take this infinitely long horn, could I fill it up with a certain amount of, say, paint? If I poured paint into this horn, could I fill it up? I could. This is how much paint I need. So, pi pints, pi quarts, pi gallons. All right, so whatever unit we're working in, I need pi of this. So it's kind of mind-boggling that I can fill up this infinite structure with a finite amount of paint. But I'm not done yet. The show goes on. Let me show you another amazing, interesting thing. And that is, let me switch colors for the dramatic appeal. What we got going here? Orange, look at that. All right. Another thing we talked about was surface area. Do you remember doing surface area? On surface area, that's why I'm switching colors here. We no longer talked about discs that went through. We talked about ribbons that wrapped around the object. And that day we developed a formula. Does this look familiar at all for surface area? The surface area of a figure was an integral, and it was 2 pi. I'm not going to show y anymore. This one's still going to go from 1 to infinity. But the formula was f of x, and then it was followed by this big square root. If you look through your notes, or your subconscious, or hopefully your conscious, you will remember this formula. Does it look familiar? Surface area? Does it?
A little bit.
A little bit.
Not really.
I remember the disc and, the washers and the
This.
ribbons.
Alright, well this was a surface area. And we actually developed that by studying that ribbon. And I remember bringing in a ribbon and wrapping things so well. So what? The function f of x in this problem I can replace because I know what the function is, 1 over x. And in the middle of this formula, I have to take the derivative of 1 over x. What is the derivative of 1 over x? Being x to the minus 1. So what's that, Gianni?
Minus 1 over x squared.
Alright, so minus 1 over x squared. That seems to be popping up a lot lately. So that is going to be squared. So when we square that, Gianni, what does that become?
1 over x to the 4th.
Right, so positive?
Yeah.
Alright, so now we have 1 plus 1 over x, not to the 4th, but 1, not 4, but 1 over x to the 4th, like you said. Alright, so let's talk about that before, if we were going to take the limit and replace this with a variable that we've defined, like t, and do our magic that we have been doing in our improper integrals, what's going to happen? Can you foresee with me not writing the whole thing out, what's going to happen to this part, 1 over x, as, well, we already know from our discussion today, what's going to happen to 1 over x.
Infinity.
All right, because it's divergent, because our p is 1. And remember the theorem said if p was equal to or less than 1, it would diverge. So this is divergent. So the whole thing diverges. Does that? So this diverges. So this means we cannot come up with a constant for the surface area like we did for the volume. So this is our volume. Remember, we could fill this horn up with paint, but we cannot cover it with paint. Does that make sense? No, it doesn't. How can we have a structure that's infinitely long? I can fill up the inside with paint, but I can never paint the outside of it.
Oh, yeah, that does not make
It
sense.
does not make sense. So Gabriel's horn is a member of a very special group
Wait,
of
is it grape? Like Gabriel?
Gabriel.
Oh, okay.
I
I
thought the R was silent.
wasn't sure if it was
It's
like
a silent
a
R.
different.
Oh, I actually didn't write it wrong.
In my language, the R is silent. All right, that's great. I love that. All right. So this Gabriel's horn, not Gabriel, not Gabriel's. Gabriel's horn is an infinitely long shape. It has a finite volume, but an infinite surface area. And that is part of a bunch of different objects that are like that. Any solid that has a finite volume and an infinite surface area is called a supersolid. I'm not making this up. So this is an example of a supersolid. See all the amazing things you can study in mathematics. So,
I'll let someone else
All
study
these
them.
super things.
supersolid again is a 3D object that has an infinite length. It has a finite volume, but it has an infinite surface area, which when you think about it too hard. What if you fill it up with paint and you fill the whole thing up with paint and you just make the horn out of a material that's porous and the paint bleeds through? Wouldn't it cover it all? Apparently not. We cannot cover up the horn. Well, there's not enough. It's an infinite surface area. It's a finite volume. So go figure. So Aaron, when you come in, you can explain it to us. All right. So we're going to have an assignment that will match our discussion with the p-value, and we also have just a couple other regular improper integrals to do. And we're going to have a snack. Maybe we'll show you when we get it set up. All right, so here's the homework. It is number 19. We're still on 8.8.
Binders
We're
are
already
bad.
into the home.
19,
My binder is up.
20, 21, 22, and 61. That's weird, but oddball, but that's the ones that we can use our new theorem on. And then in addition, we are going to do
You were just featured in the video, but you're very zoomed up. It was just your jacket.
75, 76, 77, and 78. '75, '76, '77, and '78. And those, I picked those because they have pictures. All right, let me say goodbye.
I was trying to get it on Brendan, but it wasn't working.
What?
All right, Aaron, that's it for our class. Hopefully we got this on one video that's not too long that I can't get it up, but I wanted to try to get it all in one because it was a rather short class. So hope you're okay, and hopefully see you around tomorrow. I don't have class with you, or at the field trip on Friday.
Oh yeah, yes.
Bye.